Hello everyone, welcome to the session, welcome to AS Online. In the yesterday's session, we had a discussion about transformers and as well as induction machines, right. So, we discussed a few topics also in the transformers and few, I think one topic in induction machine, right, and we did some questions based on those topics. Okay. Similarly, we will take up in this session, today's session, we will take up remaining two parts, that is DC machines and synchronous machines. Okay. I will take up one or two topics and then we will take up the questions, and in the synchronous machines also we will take up the questions. Okay. Right. So, please let me know your presence in the comment box, and if you have any doubts, please post your doubts in the comment box so that I can answer your questions. Right. Okay. As I said yesterday in the last session, every machine or every part will be having around 4 to 5 questions, and this DC machines and synchronous machines of maybe 1 or 2 questions extra. So, DC and the synchronous machines together you might be getting around 12 to 13 questions, and transformers and induction machines will be around 8 to 10 questions. Okay. So, if you take up DC machines, here you will be getting around again 5 to 6 questions. Okay. If you see the syllabus is like this, they have mentioned the syllabus like this: construction, principle of operation of both motor as well as generator and their characteristics, and speed control of DC motors and starters for the DC motors, methods of braking and efficiency of DC machines, and losses and efficiency of DC machines he has given. But mostly they are concentrating on these characteristics, okay, characteristics, applications of DC machines and speed control of DC motors. So, those are the two areas you can expect questions, at least definitely for sure you can expect a question from these two areas. Okay. So, I will be taking those two areas, but but I have listed out in different manner, like EMF and torque, EMF, torque, power equations, and then voltage and current equations. Okay. So, if you know these equations, you can answer some questions, you can answer the questions very easily. Okay. Remember, even the question is tougher also, with this EMF, torque, power equations you can answer the questions very easily. Okay. Right. So, let us get into the session very quickly, and let me know your presence. Good evening everyone. Let me take up the first one, that is EMF, torque and power equations. In the entire DC machine, these three equations are enough to solve the DC machines. These three equations are enough, even it is easy question or tough question. I am saying about problematic question. If the question is a problematic question, numerical type questions, then these three equations are enough. So, let me tell you those three equations. EMF is equals to K into phi into omega. Okay. In another way, this is actually written from where? We know EMF in the DC machine, whether it is, when I am saying it is machine, which means motor or generator, you can take up. The equation is quite valid for both the machines. So, phi P N Z by 60A. Okay. From this only we have got this one, right. What is K here? Motor constant. Flux is anyhow field flux lines. Omega is the angular rotation of the rotor. Now, after this, torque equation. So, torque equation is going to be K into phi into Ia. Okay. K into phi into Ia. Right. So, you can we generally even you can write this equation as E is proportional to flux and speed, or in another way also you can write N is directly proportional to EMF and inversely proportional to flux, all are same. Okay. Even here also torque is proportional to flux and of course proportional to armature current. Okay. Right. Now, coming to the power equation, power is equals to torque into omega. So, every rotating machine is going to develop a power, mechanical power developed by the motor or the machine is going to be the twisting moment of force into angular velocity or angular rotation. Okay. So, these three are the very important formulas with which you can solve 99.99% questions. I am speaking about problematic questions. Okay. Right. Keep these formulas in mind, and you can implement these formulas whenever you get a problem. Now, coming to the voltage current equations, we will see voltage and current equations means like they will give you generator, they will give you motor, and they will ask you to calculate back EMF in the motor or otherwise generated EMF in the generator, like that, and they will ask you what is the armature current drawn by the motor or what is the shunt current drawn by the motor, like that. So, you will get these equations by KVL and KCL of the respective machine. You will get these equations from KVL and KCL of the respective machines. Okay. So, we will get all those equations of each and every machine. Okay. Hi JE Prep, we will provide the notes also, no issues. Okay. Right. Are you speaking about this class notes? This class notes, I think it will be updated or it will be uploaded maybe in the Telegram channel or like that. Let me, I will tell you, if you please try to comment in the comment box, maybe after the live I will look into it and I will let you know. Okay. Right. So, we know that the DC machines are classified based on the excitation given to the field winding, especially I am speaking about generators. Okay. So, based on the excitation, we have separately excited, generators and self excited generators. Okay. In the self excited generators, you have shunt excitation, shunt excited generator, series excited generator, and mix also, that is shunt plus series compound generators also there. Okay. Right. So, let me write them: shunt, series and compound. Okay. So, these are the classifications of the DC generators, strictly speaking generator. If you go ahead with the motors, even separately excited motor is there, but it is better not to call self excited motors, because we will give the supply to the field winding. So, the field winding is not excited on its own. Okay. In the shunt motor, the shunt field winding is not excited by its own, the supply is taken from the external source only. Even series motor also, the source is going to activate the field winding, even compound also. So, instead of calling self excited motors, it is better to call them as shunt motors, simply series motors and compound motors. Okay. Same classification, the only thing is no need to, better not to call them as self excited motors. Okay. I hope it is clear, because the winding is not excited by its own. If the winding is if the field winding is excited by its own, you would have called it as self excited. Otherwise, what is the use of calling it as self excited, right? Okay. So, let us see the generator classifications. I am taking first generator and then we will take up motor also. If it is separately excited, every rotating machine will be having stationary part and rotating part, right? When it comes to DC machine, the stator part is of what? Field winding or not? The stator part is of field winding and rotor part is of armature winding. So, let me represent the field winding here. So, this is my field winding and this is my armature, generally armature, along with that commutator and brushes will be we can represent, but I am simply drawing those figures here. Okay. Right. So, this field winding is given with a supply, given with a separate source, V, right. So, whenever you give a supply, definitely it will drive a current and it will produce a flux lines. Okay. As the voltage is constant, current is constant, so that produced flux lines are also going to be constant. So, this field winding flux is going to be constant here in the separately excited machine. Until unless you change this voltage, current will not change, therefore, flux also will not change. Now this flux will link with the armature conductor. Of course, whenever you rotate the armature conductor, you will have a change in linkage of flux lines, and hence an EMF is going to be induced. So that you will call it as a generator, right. Now if you want to have a change in linkage of flux lines, this armature has to be rotated, na? This armature has to be rotated with the help of prime mover. So you should give the mechanical energy. So whenever you give the mechanical energy, the armature or the rotor will rotate. On the rotor you have armature conductors. So these conductors will cut these flux lines and EMF will be induced. So we call it as generated induced EMF, right. Now EMF is there. Now will it circulate the current? Will it circulate the current? We have an open circuit, right. Until unless you close the circuit, until unless you connect a load or until unless you close the circuit, the EMF cannot drive any current. So now whenever you close the circuit, EMF will drive the current, and that current will set up a flux. We call it as armature flux. Maybe quite opposite, maybe inclined, based on the the current magnitude and those things. So let me take up this armature flux, and this is main field flux. Now the interaction of these two flux lines will create a torque or not? Interaction of these two flux lines will create a torque. Okay. Now what is the use of this? What is the use of the torque here? What is the use of the torque here? The torque, the produced torque or electromagnetic torque produced in the machine is going to counter the prime mover torque to satisfy the Lenz's law. To satisfy the Lenz's law. Why? Because of prime mover torque, conductors are rotating and they are cutting the flux lines, therefore EMF is inducing. EMF always wants to oppose the very cause of its production to satisfy the Lenz's law, to obey the Lenz's law, right. Now to obey the Lenz's law, EMF is circulating a current and producing a flux. So this flux is interacting with the main field flux and creating an electromagnetic torque which is in opposite to prime mover torque. Okay, someone is moving the armature conductor in the clockwise direction, that's the reason why EMF is inducing. So EMF is telling something, EMF is EMF is driving the current and creating a flux, interacting with other flux, producing electromagnetic torque quite opposite to prime mover torque to satisfy the Lenz's law, right. So this is how each and every generator action will be the same, each and every generator action will be the same, right. So here I am going to take up the equivalent circuits and their voltage and current equations, and I am not going to repeat this operation again and again. This is a simple operation you can see in all the machines. The only thing is the connection of field winding is different, rest all other is going to be same. Okay. So let me put this equivalent circuit here. Field winding I am just representing with a resistor, armature winding I am representing with a resistor RA. We have an EMF in the armature conductors, generally it is an alternating EMF, okay. Here I am representing a constant source EG. Now these are my output terminals, okay. I am not representing the prime mover. So this is how a separately excited generator equivalent circuit looks like. So let me call this voltage as a terminal voltage. If you want to represent currents, you can represent currents, field current, and this is going to be armature current, okay. Now you can write the KVL equations and KCL equation. Generally they will ask you to calculate what is the terminal voltage developed by the generator, or what is the generated EMF induced, or what is the induced EMF in the generator. Okay. If you want to find this terminal voltage or generated EMF, you should write a KVL equation, that is it. Okay. So this EMF is going to drive the current outside, no? It is going to deliver the current outside, no? So as the current is moving from armature to the load, so the polarities across this armature resistance will be like this. Now you write a KVL. If you write a KVL, this is minus plus, so plus EG minus IARA minus Vt is equal to 0. So Eg minus IARA is equals to the terminal voltage, okay. If I connect a load, I can call this load current equals to armature current or not? Load current equals to armature current. So this is from KCL I can write. So this is my voltage equation of a separately excited generator, and this is my current equation of a separately excited generator. And even you see with the motor, okay, you can see with the motor. Let me show you with the motor. circuit is not going to change, the construction is not going to change, whether it is motor or generator, construction is same. The only thing is the type of input you are going to give to the machine is going to change. Okay. Same field winding, same armature, same construction. Okay. So, I can write here, let me show you the same resistor, and you will have a voltage source V, and this time here armature resistance, and I am calling this EMF as back EMF. Now, here we are not going to give the mechanical energy. If you want to operate it as generator, you should give the input as mechanical energy so that it can convert the mechanical energy into electrical energy. That is a generator function, right. Now, what about motor? What about motor, DC motor? It is a separately excited motor only, okay. DC motor, the function is it has to convert electrical energy into mechanical energy. So, I have to give the input as electrical energy. So, if I give the input as electrical energy, so this voltage source is going to drive the current, okay. Maybe you can call it as a line current, and which is entering into armature, so that armature current, no issues, right. So, whenever the current is circulating in the armature flux will be produced. Already there is a flux from the field side. So, the armature flux and the field flux lines both will interact, and whenever they interact you will get a torque, that is called as electromagnetic torque. Now, the torque tries to move the conductor from one place to another place, because the torque always pushes the conductor from one place to another place. If the conductor is moving in the presence of flux lines, that will cut the flux lines, those conductors will cut the flux lines. Now, later EMF will be induced, right. So, first a torque will be induced and then later EMF will be induced, right. Okay. So, this is the back EMF, and we can write the KVL equation here as, if you write KVL equation, it looks like this, plus V minus IARA minus EB is equal to 0. So, V minus IARA is equals to back EMF. So, this is my voltage equation, and the current equation is going to be what? Line current and armature current both are going to be same. In generator, generally you can call it as load current, in motor you can call it as line current. Okay. So, there is a voltage and current equation of both generator and separately excited generator, separately excited motor. Okay. I wanted to tell you one point here when it comes to the motor equation. You just, the voltage equation, you just multiply with current. If you can multiply with current, this equation on both the sides, armature current, I can rewrite this equation as V into IA minus IA square into RA is equals to, this is the mechanical power, EB into IA is called as mechanical power developed by the motor. Okay. Now, they will ask you, when will you get maximum mechanical power, okay, or what is the condition for maximum mechanical power developed by the motor? You just differentiate the mechanical power, okay, differentiate the mechanical power with respect to variable quantity. What is the variable quantity here? Armature current, and equate to 0. So, if you differentiate, you will get this one as V minus 2IARA, of course, is equals to 0. So, you will get V is equals to 2 times RA, or IA is equals to V is equals to 2 times IARA, no? Okay. Okay. Right. So, you solve this and you will end up with the condition. You can take up a resistance condition or current condition, whatever the thing you can take up, and you try to substitute in the voltage equation. You try to substitute, after getting this, you try to substitute in the voltage equation, so that you will get end of the day, I am telling you this, okay, right. When the voltage is half of the back EMF, when the voltage is half of the back EMF, you will get the maximum mechanical power. When the voltage, when the applied voltage is equals to half of the back EMF, you will get maximum mechanical power. This is very, very important condition. Okay, please remember that. And if you solve efficiency during the maximum mechanical power condition, if you solve the efficiency produced by the motor, you will get the efficiency. It is not maximum efficiency, it is the efficiency at maximum mechanical power, not maximum efficiency. At maximum mechanical power, it will be, if you solve it, you will get it as EB by V. It is like output voltage divided by input voltage, output power by input power if you do it, but end of the day this is the formula you are going to get. Okay. I hope these points are clear for you, and these are very important conditions, and the efficiency during maximum mechanical power. I am repeating once again, this is not maximum efficiency, this is the efficiency at maximum mechanical power condition. Okay? Right. So, that is that is quite valid for any motor, that is quite valid for any DC motor. Now, let us have a look at shunt machine. Okay. Shunt means parallel, that means your field winding should be connected in parallel to the armature winding. Okay. So, I am not writing the winding here, I am directly writing the equivalent parameters. Shunt winding equivalent parameters I am writing it as RSH, armature winding parameter I am writing it as RA, and this is going to be, if you call it as generated EMF, EG, and this is the load. Okay, you can take up it as VT. Now, if you see the voltage and current equations, EG minus IARA is equals to terminal voltage. Now, this armature is going to deliver the current, right, and that is going to be diverted into load and also shunt field winding. So, if you apply a KCL at this junction, the sum of leaving currents equals to entering currents or not, or sum of entering currents equals to leaving currents or not. IA is equals to IL plus ISH. Okay. So, these are the voltage and current equations of the shunt generator. Right. Similarly, for motor if you see, this is for generator, and for shunt motor, you need to apply voltage source here. So, if you apply voltage source, current direction will be reverse or not? IL will be entering into the machine. So, IL enters here and current divides. So, I can say KCL is going to be IL is entering current, dividing current is what? IA and ISH. Okay. Now, what about the KVL equation? V minus IARA is equals to back EMF. Of course, if you want to represent brush drop, you can represent brush drop also. Okay. So, these are the motor current and voltage equations. Now, they will ask the questions on either this or otherwise they will ask the questions on characteristics of generators or motors. If you look at characteristics of generators, shunt generators, if you look at characteristics of generators, generally the questions will be on external characteristics, that is load voltage or terminal voltage versus load current. Okay. Right. Armature current, it is better to take up armature current. The external characteristics will be drawn between VT and IA. Okay. See, if the load is going to be increases, definitely armature current is going to be increases or not? Who has to supply? Armature has to supply. So, armature current is going to increase, right. If armature current increases, the resistance drop in the armature resistance drop also increases. If the resistance drop increases here, if armature current increases, the resistance drop increases. If the resistance drop increases, the terminal voltage is going to fall. So, under no load, the armature current is approximately minimum. So, I can say that the no load characteristics looks like this. Now, during load condition, as the current increases, the drop is increasing. If the drop increases, terminal voltage slightly falls. there won't be much fall in the voltage, terminal voltage, because armature resistance is a very small value. Even though armature current is a full load current, maybe 50 amperes, 50 into 0.1 you will get hardly 5 volts or 10 volts drop. So terminal voltage will not fall much. Okay, almost constant characteristics will be there, almost slightly there will be decrement in terminal voltage, but almost it is going to be constant. But if you go beyond full load current, what is going to happen? If the current is going to be beyond full load current, when the current magnitude increases, the flux in the armature also increases. Therefore, armature flux is going to interact with the main field flux. It is going to interact with the main field flux, and that leads to huge amount of armature reaction, which might lead to reduction in resultant flux. Whenever the flux levels increases in the armature, definitely interactions also increases, interaction between main field and armature flux increases, and which leads to reduction in net flux in the machine. If the net flux reduces, then here what will happen? EMF generation decreases. If EMF generation decreases, terminal voltage also falls. You can see the sharp fall, or almost a sharp fall like this. The drooping characteristics you can see in the shunt generator above the full load current. Okay. So drooping characteristics you can find in the shunt generator. Till full load it is almost constant. More than full load you can find drooping characteristics. Okay. So this is the reason why shunt generators should operate till full load. Now as the voltage is almost constant, the applications of shunt generator, where we will use, as voltage is constant, generally we will use it as like a voltage source or for battery charging purpose. For battery charging purpose. Even small distance street lighting also, for street lighting purpose also you can use. So they can ask the questions on applications, characteristics, voltage and current equations. Okay. Similarly, you can take up characteristics of shunt motor. Okay. So you can take up the characteristics between speed and current, torque and current, speed and torque also. There are three characteristics. Speed and current, speed and torque almost same. Okay. So let me show you here. Armature current, speed versus armature current. We know the equation N is proportional to back EMF and inversely proportional to flux. Na? In the shunt machine, you see, if the applied voltage is constant, the voltage across the shunt field winding is also constant or not? If the applied voltage is constant, the voltage across the shunt field winding is constant. As long as this is going to be constant, definitely the current flowing through the shunt field winding is also constant, and hence flux produced in the shunt machine is going to be constant. So shunt motor is a constant flux motor. Shunt motor is a constant flux motor. Okay, right. So if you take up this as constant, now the speed is directly proportional to back EMF. I can write the back EMF as, how can I write the back EMF? V minus IARA. Okay. So under no load condition, the armature current is a very small value. Okay. The drop is also going to be very small. Now, if you neglect this one, speed is directly proportional to applied voltage, rated voltage. Or I can write this as almost, rated speed, or the speed proportional to rated voltage. Okay. Now, whenever you increase the load on the motor, that is definitely it will draw more current. So if the current increases, this drop is going to increase. If this drop is going to increase, this resultant value slightly falls. You don't expect much fall. Why? Because again the same reason. Resistances are very, very small. Even though the current is full load current into small resistance will be resulting a small drop, and hence the fall in the speed is almost negligible. So you will get a characteristics again the same as like this characteristics. Generator is going to have almost constant terminal voltage, motor is going to have almost constant speed. Motor is going to have almost constant speed. So shunt motor, you can also say shunt motor is approximately is going to produce constant speed from no load to full load. Okay. So this is the this is the characteristics of a shunt motor, which is between speed and current. If you see between torque and current, we know torque is proportional to flux and current, na? We said that this flux is constant here. We cannot change because if the voltage is constant, flux is constant, so you can't change. The only change is here, whenever the load changes, only armature current changes. So under no load, current is small. If the load increases, current increases. So if the current increases, definitely torque also increases. So it looks like linearly proportional. So you can draw a graph or a line like this. Shunt motor torque versus armature current characteristics looks like linear characteristics. Okay. Shunt motor torque versus armature current characteristics are linear characteristics. So based on this, they will ask the question, if a shunt motor is producing or shunt motor is developing a torque of 100 Newton meters at a current of 10 amperes, what will be the torque developed by the same motor if the current increases by maybe double, if the current increases 2 times. So just write T2 by T1 is equal to I2 by I1, you just substitute, you will get the answer. Such kind of simple questions you can expect. Okay. Either they will ask about the graphs or they will ask about this equation based questions, okay, or sometimes they will ask the questions on applications also. So if you look at torque versus current, for small currents the torque produced is also small, for moderate currents the torque produced is also small. I can say at the beginning, generally at the beginning, the current drawn by the motor under no load condition, I can say very small. So I can say the torque developed by the motor is approximately a small value. So you cannot use this shunt motor for driving a huge amount of loads or bulk loads like cranes or otherwise electric locomotives. For that kind of loads or bulk loads you cannot use this motor. Generally for moderately or low to moderate torque values or wherever low to moderate torques are required, that at that point you can use. Okay. Maybe fans, blowers, lathe machines. Okay. So these are some applications of shunt motor. Okay. So these are quite frequently repeated questions. Right. I hope it is clear. Please let me know if you have any doubt. Is it clear, guys? Now let us take up series machine. Okay. So I am not drawing again the winding and all those things, and directly I am putting the equivalent circuit. Armature winding resistance, I am taking with generator first. Armature resistance, as I am calling it as generator EG, and the winding must be in series with armature. So this is going to be RSC, and this is my load. Okay. So the voltage across the load you can call it as terminal voltage. This is the armature current and this is the series field current and this is load current. So if you see the current equation, or if you see at any junction or at any simple node, there is no current division at all. So armature current, whatever the current which is circulating in armature, the same current is circulating through series field winding and the same current is circulating through load also. So the armature current, series field current, load current are going to be same. And if you see the voltage equation, generated EMF minus this drop is equal to voltage, na? It is like input minus drop is equal to output. Okay. So, I can write Eg minus IARA and ISC RSC. ISC and IA both are same na, so let me write it as RA plus RSC is equals to terminal voltage. Okay. So, this is my these are the current and voltage equations of series generator. Okay. If you see the external characteristics of series generator, the terminal voltage versus armature current. Yeah. Under no load condition, no load means it is an open circuit, do not put a load. If there is an open circuit, do you have a current circulation here? Not possible. Do you have a current circulation here? Not possible. Okay. So, if it is not possible, you cannot draw no load characteristics. You cannot draw no load characteristics. You cannot draw internal characteristics also. The only possibility is load characteristics. You go ahead with the IL. You go ahead with the IL. So, if you put a load, then increase load or put a load in parallel. Put a load in parallel. So, if you increase the load, then definitely who has to drive the current, who has to deliver the current? Armature, na? Right. So, you see now, when the load increases, the armature current increases. If the armature current increases, this drop increases. If this drop increases, this difference will decrease and hence terminal voltage looks like false. If you look at this equation, okay, right. But actually what is going to happen is, whenever the load is increasing, here load current is increasing, which means series field current is increasing. If the series field current increases, series field flux also increases. If the series field flux increases, what will happen? If the main field flux increases, what will happen? Generated EMF will increase, na? Generated EMF will increase. If the generated EMF increases, terminal voltage increases. Okay. If you look at this way, as load increases, armature current is increasing, drop is increasing, and it might be falling, it might be looking like falling characteristics, but actually this is not true. If you see here, the flux increment is going to increase the EMF a lot. Okay. So, forget about this drop is very, very small. So, the increment in flux will increase a huge increment in EMF, and the terminal voltage also going to be increases. Okay. Right. That is the reason why the characteristics are going to be not falling characteristics, they are actually rising characteristics. For series generator, the characteristics are called as rising characteristics, whereas shunt generator, if you go more than full load, it is falling, even under from no load to full load also slightly falling, but this is they are called as rising characteristics. Okay. Right. Coming to no load and internal characteristics, we cannot draw them, it is just an imagination. Okay. We cannot draw them, it is just an imagination, because under no load, when there is no closed circuit, how can you expect? Right. There is no current flow at all, how can you expect? Just an imagination. So, these are external characteristics which are generally rising characteristics. Okay. So, because of this reason, we can apply or we can use this series generator as booster. You can use it as booster or boosting the voltage in the HVDC transmission line. Booster in HVDC transmission line. In HVDC lines, we can use it as booster, because if the load increases, current increases, the same phenomenon, terminal voltage increases. Actually, the receiving end voltage should fall, but because of this series generator existence, the terminal voltage will increase. Okay. Right. So, this is one of the main application of the series generator. Now, if you see the motor, series motor, what about current equation and voltage equations? If you connect a voltage source here, line current, series field current and armature current, all are same or not? All are same. What about voltage equation? V minus Ia of Ra plus Rsc is equals to Eb. V minus Ia of Ra plus Rsc is equals to Eb. Okay. So these are voltage and current equations. Now if you see the characteristics, speed versus armature current characteristics. Okay. We know speed is directly proportional to back EMF and inversely proportional to flux. Okay. Do you call a series motor as a constant flux motor? If the load changes, armature current changes. If the armature current changes, series field current changes. If the series field current changes, series field flux also changes. Na? So series motor is not a constant flux motor, it is a variable flux motor. Okay. Right. So as the load increases here, armature current increases. So series field flux also increases. Right. Now this increment in flux will be leading to fall in speed. So under no load condition, you see, the current drawn by the motor is very less. If the current is very less, this flux is also going to be very less. If this flux is very less, the resultant speed looks like very high, or we can also say that infinite amount of speed, or the series motor is going to rotate at dangerously high speed under no load condition. This is the reason why we do not operate the series motor at no load conditions. We should put some load. That's why for for trains, bogies are the loads for series motor, or the motive, the bogies are the loads, I can say. Always there should be a load on the series motor, right? Otherwise it will rotate at highly dangerous speed. Now whenever you increase the load, the speed falls quickly here like this. Okay. Till full load you can write, and after full load what happens? It's almost constant. After full load, the characteristics looks like almost constant, or slightly follows, or slightly looks like shunt motor characteristics. Why? Because if the current is more than the full load current, by the time series field winding is going to be saturated. The field winding is going to be saturated. If the field winding is going to be saturated, this flux is going to be constant now. Now the speed depends only on this back EMF factor, V minus IARA factor. Okay. So that is the reason why this is almost going to be constant. Okay. So this curve we call, what do you call this curve? Rectangular hyperbola, na? Rectangular hyperbola. Similarly, you can take up torque versus current. Torque versus current, if you see, torque is proportional to flux and current. Here the flux is proportional to armature current, na? So armature current into armature current, you will get armature current square, Ia square. Okay. So they will ask the questions on this. A series motor is producing a torque of 240 Newton meters for a current of 10 amperes. If the current is increased by some more 2 amperes, or if the current is increased to 12 amperes, what is the torque produced by the series motor? That kind of questions they will ask. Okay. If you see, for small amount of current, 1 square is a small value, 2 square it's 4, 3 amperes, 3 square 9, 4 amperes, 4 square 16. As the current increases, the square of that value definitely increases, na? So torque value increases. So at the small values of current, the torque might be very low, but after some time the torque is going to be increases rapidly like this. Okay. Parabola, it looks like parabola. Now after full load, what will happen? After full load, the same thing. The series field winding is going to be saturated. If the field winding is going to be saturated, now the flux is constant. If the flux is constant, the torque is depending only on armature current. If the torque depends only on armature current, what happens? It looks like linear characteristics. So series motor after saturation, the characteristics of series motor after saturation looks like shunt motor characteristics. Okay. So these are linear and this is non-linear. Of course, this is parabola you can write. So, they will ask you the names also, what are the torque versus armature current characteristics, how the torque versus armature current characteristics looks like of a series motor, okay. Before saturation and after saturation also they will ask. Okay. I hope it is clear. If you have any doubt, please let me know. Tell me, my dear. All right. Similarly, for compound motor, there is a one important point in compound generators and motors. Compound means what? It is a mixture, right? Shunt plus series. One winding in parallel with the armature and the other winding should be in series with this combination, armature and field winding. Okay. So, you can have compound, you can have cumulative compound and differential compound. Cumulative compound and differential compound. I am not writing the equations or the diagrams, it is enough, the same pictures you will get, but extra one more winding extra, right. So, here the point is the resultant flux is going to be addition of main field flux, or otherwise you can also call it as shunt field flux plus series field flux. In this case, the series field flux may oppose the shunt field flux. So, on the pole core you should place two windings such that if the two windings are going to give you the resultant flux, increased resultant flux, that is called as cumulative. If the two windings are going to give you the resultant flux as a low flux, then that is called as a differential machine, okay, right. So, based on this you can take up the characteristics of compound generator looks like almost similar to shunt generator, and the characteristics of compound motor characteristics will be like this. I am taking motor characteristics, cumulative motor and differential motor. Okay. Let me take up speed versus current. Certain speed is there. Now, you see no load. So, if you increase the load, what will happen? Definitely the series field flux, there is a chance of increment in series field flux. So, resultant flux increases. If the resultant flux increases, speed will reduce. So, for cumulative compound, it looks like this. Okay. What about differential compound? Whenever the load increases, definitely series field flux increases. So, opposition increases, net resultant flux falls. If the net resultant flux falls, what about speed? Speed will increase, right. So, the differential compound motor speed characteristics might be it goes like this. This is for differential compound motor, right. Out of all the motors, this is the only one motor which is having full load speed greater than the no load speed. Remaining all motors will have full load speed as less than the no load speed. All motors, all DC motors will be having full load speed as less than the no load speed, but differential compound motor except differential compound motor. So, differential compound motor you see full load speed is greater than the no load speed. That is the reason why differential compound motor can have a chances of getting negative speed regulation, okay, negative speed regulation. For remaining all motors it will be positive speed regulation. So, these are some points about voltage and current equations and the characteristics, okay, right. Let us take up some questions on DC motor. Right. Look at this question. A generator is rated at 2 kilowatts, 200 volts DC. It can supply load current of how much? He has given generator, power equation he has given, and voltage he has given. maybe he did not mention any separately excited or shunt generator, but anyhow at load he has mentioned that it is going to be the load voltage you can take up it as 200 volts, and it is going to drive load the power of how much? 2 kilowatts. Okay. You know P and you know V. Can't you calculate the load current here? Power is equals to voltage into current, na? Simply. So, the current will be how much now? P by V. So, 2 into 10 to the power of 3, 2 kilowatts divided by 200 volts. How much you are going to get? 10 amperes or not? C could be the correct answer. Yes or no? Very good, JE. Right. Let us see one more question. In a DC generator, the critical resistance refers to the resistance of. Okay. So, here resistance, critical resistance he is speaking about. Generally, we have conditions to build up the EMF, na? Conditions to build up the EMF. There must be residual flux, right? There must be the prime mover speeds should be greater than the critical speed, and the field resistance should be less than the critical resistance. Like that, we have conditions to build the voltage in the generators. Okay, in the self-excited generators. Is it associated with what? Critical resistance is associated with field winding resistance, not load, not armature, not brushes. It is associated with field winding. Yes or no? The type of DC generator used for arc welding. The type of DC generator used for arc welding. I said shunt generator application, series generator application, okay, but not compound generator application, wantedly, because we have a application here. For arc welding, we generally use what kind of generator? Cumulative compound or differential compound? We go with differential compound. Why? Because net flux is what? Net flux is phi SH minus phi E. So, whenever you put that welding rod, that means what you are closing the circuit, load circuit, definitely load current increases. When you put the welding rod, load current increases. If the load current increases, series field current increases, series field flux increases. If the series field flux increases, the resultant flux is decreasing. If the resultant flux decreases, EMF decreases. If the EMF decreases, terminal voltage falls. That means, if you put a welding rod or wherever you wanted to do the welding, if you put a welding rod and you just leave it, nothing will happen. Because after certain time, the terminal voltage is falling to 0, so nothing will happen. So, you do not get the sparking continuously. That is the reason why we use differential compound motor, differential compound generator. If you use cumulative compound generator, what will happen? Resultant flux is equal to phi SH plus phi SC, na? Whenever you touch the welding rod, series field current increases, phi SC increases, resultant flux increases. If the resultant flux increases, generated EMF increases, terminal voltage also increases. Yes or no? If the terminal voltage increases, it continues. That means that potential difference increases. Now, that voltage drives large amount of current into that job or welding rod, and the sparking continues. It should not happen, na? It should not happen. So, we do not prefer cumulative compound generator. We prefer only differential compound generator for welding purpose. Cumulative compound generator, generally we can do the same applications of shunt generator only, street lighting or battery charging. Okay? Now, look at this one. The terminal voltage of a DC shunt generator on loading. Terminal voltage of DC shunt generator on loading. So, whenever you are increasing the load, there is a slight fall, na? Increases slightly, will it increase? No. Increases sharply? No. Will it increase? Definitely not. Decreases slightly. Yes or no? Because of armature resistance drop, you can see a slight fall. Look at this one. Which of the following motors has a high starting torque? We have seen shunt motor torque versus current characteristics. I said you do not get much torque. Okay. But look at DC series motor, torque is proportional to current square, na? So if there is an increment in current, earlier if I have 10 amperes, 10 square 100, if I make it just 2 amperes, so 12 square it will be 144, 100 Newton meters and 144 Newton meters. There is a huge change now. So you get a chance, you get a more torque production in the series motor rather than shunt motor. Anyhow, induction motor is going to be a small starting torque only. And coming to synchronous motor is not at all self-starting motor. So the starting torque in the synchronous motor will be 0, to say exactly. DC motors are self-starting. DC motors are self-starting. What about this question? A DC series motor is best suited for series motor. It can produce lot of amount of torque. So it is suitable for what? Huge huge torque load applications. I can say cranes, hoists is the best option. Electric locomotives, the best option. Okay. Right. See, the ratio EB by VT of a DC motor is an indication of what? Output by input, na? Back EMF by voltage. It's like output by input. So it indicates efficiency. It indicates efficiency. Right. Now you see, the mechanical power developed by the armature of a DC motor is equal to P mechanical. We have solved the equation. P mechanical is equal to what? EB into IA. Armature current into back EMF. Option A is the correct answer. Okay. Now look at this one. DC shunt motors are commonly used in shunt motors. Where we can use? Will you use it in traction? No. Will you use it in elevators? Generally not. Cranes of huge load only. Traction is also huge load. Generally you can use fans, blowers, lathe machines, moderately torque required or moderate torque loads only. Look at this one. A shunt generator running at 1000 RPM has a generated EMF of 100 volts. Let me mark this as N1. If the speed increases to 1200 RPM, then the generated EMF will be shunt generator, flux is constant. So we know EMF is proportional to flux and speed, na? So I can write EMF is directly proportional to speed because flux is constant. So now I can write, here he is asking E2, na? So E2 divided by E1 is equals to N2 divided by N1. So what can I write? E2 is asking, na? N2 is 1200, N1 is 1000 into E1 how much? 100. How much you get? If the speed increases, he is increasing the speed from 1000 RPM to 1200. So definitely EMF also increases from 100 volts to some value. So answer must be greater than 100. All are greater than only. All are greater than 100. So you can take up the best answer. 120 volts is the correct answer. Right. So this is all about DC machines. Okay. Very good. So let us have a look at synchronous machines. In the synchronous machine, there is no particular topic they are covering. They are covering all the areas, right from construction, windings, and then armature reaction, and then the V curves and inverted V curves. They are touching each and every area. So you will be getting one question at least in the synchronous machines. Okay. So that's the reason why I am not taking any particular topic here. I will take up directly the questions. Okay. So these are very popular questions I am going to take up. These are the very popular question or frequently asked kind of questions. Can you answer this? A 4-pole 1500 RPM alternator will generate EMF at. It's an alternator. Is asking frequency of generation. How do you calculate generally frequency of generation? F is equals to Pn by 120. What is this N? Don't call it as synchronous speed, it is actually relative speed. Relative speed between what? Relative speed between flux and conductor. Generally, in alternator, flux is of rotating quantity. Conductor we will be placing on armature. So the conductor speed is 0 RPM. Flux speed is how much? Flux speed is how much? Prime mover speed or rotor speed. So generally the rotor speed, we rotate the rotor at RMF speed. We will rotate the rotor at RMF speed, that is synchronous speed. So F is equals to number of poles are 4 and relative speed I can take up it as 1500. 1500, what is this 1500? It is a rotor speed only, prime mover speed only. So 1500 minus the conductor speed 0 divided by 120. So if you solve it, you will get how much? 4 3s 50, yeah? 50 hertz is the answer. Okay. Right. Look at this one. The angle between rotating stator flux and rotor poles is called. Okay. Will you call it as torque angle or obtuse angle, synchronizing angle or power factor angle? Definitely power factor angle is not the answer, right? Obtuse angle, no. Torque angle or synchronizing angle, how do you call? Generally in the generator rotor leads the, generally rotor poles leads the stator poles. So if you draw, it looks like this. So if I call this as rotor rotates at synchronous speed. I can take up this as north pole, and on the stator south pole has to be formed, and now this is how you can have a magnetic locking between the stator and rotor. Now this is my stator field axis and this is my rotor field axis. The angle between the stator field and rotor field, we call it as torque angle, not the load angle. Load angle is between resultant flux and rotor flux. Load angle is between resultant flux and rotor flux. Torque angle is in between stator flux and rotor flux. So the answer is A. Okay. Now look at this one. Usually the number of poles in the turbo alternator, we generally use this, turbo alternator is nothing but, we take up for steam power plants or thermal power plants. Okay. Generally these steam power plants, thermal power plants are going to operate at high speed. What is the speed? High speed means what is the speed? Generally Ns is equals to 120 F by P. So generally if you want to generate 50 hertz frequency, the numerator is going to be 6000, right? If you want to get the speed as high value, the poles must be minimum, na? The poles must be minimum. So minimum number of poles are what? 2. So if you take up 2, the answer will be 3000 RPM. So for high speed, the number of poles generally 2. For turbo alternators, it will be 2. Now look at the next question. The armature reaction affects the dash when the load on the alternator is increased. Will it affect the rotor speed? Will it affect the no load losses? Will it affect the frequency of armature? Will it affect the terminal voltage? Okay. EMF is proportional to flux, na? This resultant flux is a combination of main field flux plus or minus armature flux. Okay, this is what armature reaction. Armature reaction means what? Interaction of armature flux with the main field flux. The interaction may be leading to decrement in resultant flux, may be leading to increment in resultant flux, may be deviating in resultant flux. Okay, so you can have different of types based on the load nature, right? So when the load increases, which flux will change? When the load on the alternator is going to be increases, which flux will change? Will it change main field flux? No. This depends upon excitation. Na? This depends upon excitation. What about this one? Armature flux depends upon load. So if the load increases, armature flux increases. Now this is going to change definitely the resultant flux. If the resultant flux changes, EMF changes. If the EMF changes, terminal voltage will change. So the terminal voltage is going to be the most influenced parameter or most influenced quantity, most affected quantity. Okay. Right. Look at this one. A winding which has equal number of slots and poles. So, or he is saying that slots equal to poles is called. Generally, how do you calculate pole pitch? Pole pitch is the ratio of slots per pole. Okay. He is saying that they are equal. So which means 1. You are placing the winding in one slot only. Slots per pole or pole pitch there only. Means if you have many slots like this, you are placing the winding here itself, you are placing the winding here itself, rest all the slots in the pole pitch, it is like they are going to be what I can say empty, it looks like empty. Okay. What is a winding? Will you call it as a full pitched winding? Will you call it as a concentrated winding? Will you call it as a short pitched winding or distributed winding? Okay. What do you call? Oh, sorry, he said slots and poles are equal. Na? Okay, slots are okay. So under each pole we have a slot. Under each pole we have a slot. What will you call? Will you call full pitched winding or concentrated winding? If the winding is distributed in each and every slot, you can take up it as distributed winding. Okay. Generally distributed short pitched winding is also distributed winding. The only thing is if the winding what I can say distance is less than the 180 degrees angle, you can call it as short pitched winding. If coil span is 180 degrees, it is a full pitched winding. If the coil span is less than 180 degrees electrical, it is short pitched winding. Now what do you call this? Will you call it as like a concentrated winding or full pitched winding? Can you answer me? You will go with full pitched winding or concentrated winding? You can answer me in the comment box. I will reply and I will give you the explanation also. Okay. Look at this one. The rotor in an alternator requires, will it requires pulsed DC, triangular wave, AC supply or DC supply? Alternator stator is of what? You will have a armature winding. Rotor, you can have either salient pole rotor or otherwise cylindrical pole rotor. So the rotor in an alternator requires what? We give a DC supply, na? We give a DC supply, constant supply. Look at this one. Synchronous motor when used for power factor improvement should be synchronous motor when used for power factor improvement. So an overexcited synchronous motor is going to deliver the reactive power, na? Right. For power factor improvement, we call the we will use the synchronous motor as a synchronous condenser, right. So it has to be operated at overexcitation, generally no load purpose, because if you are putting some load, synchronous motor will draw some active power and that will be supplied to the mechanical load. So if you are using for power factor improvement, no need of putting a load on that one. So generally it is no load operation, operated under no load but not under excitation, it should be over excitation. Okay, it should be over excitation. Now look at this one. Which of the following are the disadvantages of synchronous motors? Which of the following are the disadvantages of synchronous motors? Usually they operate with higher efficiencies, requires DC excitation, ability to control the power factor, electromagnetic power varies linearly with voltage. Here ability to control the power factor is not an advantage, it is actually it's not a disadvantage, it is actually an advantage. He is asking disadvantage, right? Disadvantage, what is a disadvantage? It is not a self-starting motor and you require supply to the stator and rotor, okay, right. So that kind of things are disadvantage. So requires DC excitation because you are giving already supply to the stator and it requires one more supply. So the best answer is here requires DC excitation. That is a drawback. Look at this one. The armature current of synchronous motor has large values for high excitation, medium excitation, both low and high excitation, low excitation. Excitation versus armature current characteristics. Armature current versus excitation characteristics. How it looks like? Excitation is under excitation. So, the generally current is going to be large current. If the excitation increases, current decreases. Okay. Now, this is normal excitation. If the excitation increases more than the normal, again the current increases. It looks like V curves. Na? For inverted V, you get for inverted V curves, you will get for power factor versus excitation. So, the armature current of synchronous motor has large value. So, you are getting a large value at a lesser excitation and large excitation. At under excitation, you are getting an armature current of large value, and at over excitation also large currents are possible. So, both low and high excitation it is possible. Okay. So, these are the questions which you can expect. Okay, let us see the question which we left, whether it is full pitched winding or short pitched winding, because slots and poles both are equal. Okay. So, will you call it as full pitched winding or short what is the other one? Full pitched and concentrated, I think so. That we left, I think so. We will see that. How many of you will answer? Try to post your answer in the comment box and we will see, and I will give you the reply. Okay. Thank you. Thank you so much. Have a nice day. Bye.